Hi students. In the last lecture, I have discussed self-induction and mutual induction. Let us now see problems. See the first one. An inductor of inductance cell is connected to an ideal battery of EMF E. Find the energy stored in the inductor if current is I. Find the current in the circuit as a function of time. See how to start. So first the given data. So connecting an inductor across an ideal battery. Assume initially circuit was open, no current in circuit. EMF is given as E and inductance it is. Now see, once we close the switch, now we have to focus current as a function of time. Also, also we have to find out energy stored in the inductor, right? Let us see what happens when switch is closed. So once the switch is closed, current starts increasing from zero, right? And we are knowing that role of inductor is to oppose change in current. That means if current is increasing, it tries to decrease it. If current is decreasing, it tries to increase it, right? Now here current is increasing. So since current is increasing, it tries to oppose that. Okay. And you can see EMF induced across the inductor, that is given by EMF induced across inductors. I am focusing only modulus value. It is equal to L into di by dt. Okay. So this is now EMF induced. That means across the inductor. This is now EMF. And we are knowing that across the inductor, EMF is equal to battery's EMF. Right? That means this value should be equal to E. I am repeating. In the circuit, we have only battery and inductor. So EMF across the inductor should be equal to battery EMF. But we are knowing that EMF across inductor is given by L into di by dt. That's why this value should be equal to battery EMF. Okay. Let us see now. Let us take at one instant current in circuit is I. So we are taking current is I at one instant. Then, so we have learned that if I current is passing through the battery, then power delivered by the battery is equal to EMF of the battery into current. So this is what we have learned earlier, right? So this is the power delivered by battery, or you can say this is the rate at which energy is delivered to inductor, right? Both are same. That means now I can write this as, since E equal to L di by dt, it is now L I di by dt, right? This is the rate at which it is the rate at which energy is delivered by the battery to the inductor. Means it is power. Okay. It is the rate at which energy is delivered by the battery to the inductor, which is nothing but power delivered by the battery, which is equal to the rate at which energy is stored in the inductor. Okay. That means now this is equal to du by dt, where u stands for potential energy of the inductor. This is the rate at which its potential energy is increasing. Okay. Let us now focus from that what I can write. So we can write here du equal to, it is Li di, right? Now integrate. Initially, when there was no current, there was no potential energy stored in the inductor. So when I equal to 0, potential energy was 0. When current is I, current potential energy is out. Sorry, it is you. Now simplify this. See what we get. Potential energy is equal to Li di. L is a constant, take outside. Integration of I di. That gives I square by 2, right? So finally we are going to get a half Li square. Means if I current is passing, then potential energy stored in the inductor is given by half Li square. Okay. Next. See, in this we have to calculate what is current as a function of time, right? We have to get current as a function of time. Then see how to get it. So if you observe here, what we got, it is EMF of the battery is equal to the EMF across the inductor. So L di by dt is equal to E. So I'm taking that here. L di by dt, that is equal to E. Now from this we can write di is equal to E by N into dt, right? Now integrate. Here you can see battery's EMF is a constant. Inductance of the inductor is also constant, right? When time t equal to 0, current was 0, right? At time t, we want to find out current. Then see what we get. I equal to E upon N into T, right? So this is a current in the inductor as a function of time. Okay. Suppose you want to plot a graph, then see graph will be, it is y equal to mx, right? It is a straight line passing through origin. So I'm plotting here graph current versus time. So you may expect questions even by giving graph like this, asking questions based on graph current versus time. So graph is now, it is a passing through origin straight line, passing through origin, and you can see slope equal to E by N. So we may expect questions based on the graphs, right? Next. And if we use this result here, then we can write potential energy as a function of time. See carefully. Potential energy, we got a half Li square, half Li square. In the place of 5, I am writing here this result, E by N into T, half Li square. This is now, see what we are going to get, E square by 2L into T. The T square, right? It is T square. That means if you plot a graph that is for potential energy versus time, it will be parabolic, right? It is of the form y equal to something into x square. So if you plot a graph for potential energy versus time. This will be parabolic. Our graph is like this. It is parabolic, right? So like this, we can calculate current as a function of time, potential energy as a function of time, and potential energy in terms of current. Half L is half L I square. Okay. Let us see next problem. Right. Coming to here. Find the equivalent inductance if inductors are connected in series across an ideal battery. Also find the equivalent inductance if they are connected in parallel combination across an ideal battery. Okay, let us see how to start. So first of all, we have to focus the parallel combination. Let us consider inductors are connected. Inductors are connected in series combination across an ideal battery. Okay. Suppose its EMF equal to E, battery's EMF, and their inductances L1 and L. So initially there was no current in circuit. Okay. Now once we are closing the switch, current starts flowing, and now current starts increasing, right? Starts increasing from 0. Since the current is changing and EMF is induced across the inductors, right? Then we can say that the EMF induced across the first inductor plus across second inductor, the sum should be equal to the EMF of the battery. So I'm writing here. So here what happens is current is now increasing, right? Since the current is increasing, if you want to replace inductors with batteries, we have to replace like this, positive and negative. And this also positive and negative because the current is increasing. So I'm writing condition battery's EMF should be equal to sum of the EMFs that are induced across the inductors, which is equal to L1 into di by dt. Since they are in series combination, same current flows. That's why di by dt is same. L2 into di by dt. Now question is, for this combination, what is the equivalent inductance? See, what is the meaning of that? If we want to replace these two inductors with a single inductor, I'm drawing here. If you want to replace both the inductors with a single inductor, and if we connect the same battery, then the EMF must be equal to again same. Okay. So for same change in current, condition 1, for same change in current, now we have to get same EMF. That means if the CZ, E must be equal to, it is L into di by dt. So I'm repeating once. If you want to replace these two inductors with a single inductor, for same change in current, we have to get the same EMF. Therefore, L di by dt is equal to EMF of the battery. Now remind just a calculation, right? Throughout di by dt gets cancelled. Therefore, L equal to, it is L1 plus L2. This is equivalent inductance for series combination. Let us now focus parallel combination. So consider two inductors which are in parallel across an ideal battery. Now see how much current flows here. Initially switch was open. Now once the switch is closed, current flows in the circuit. Let us take now this current is I. Let us take this is L1 inductance and this is L2. Since these two are in parallel combination, current divides. Let us take it as I1 and this is I2. Right? So the first condition is I equal to I1 plus I2. Right? And if you observe carefully, since current is changing, an EMF is induced across the inductor and these two are in parallel to the back. That means EMF induced in this one should be equal to battery's EMF. Same thing, the EMF induced across this should be equal to battery's EMF. That means we can say that it is, I'm writing here, L1 di1 by dt is equal to L2 di2 by dt should be equal to battery's EMF, right? Next, now differentiate this and see what we get. di by dt is equal to di1 by dt plus di2 by dt. Okay. Now write in the place of di1 by dt E by L1. In the place of di2 by dt E by L. Now we want to replace these two inductors with a single inductor so that for same change in the current we have to get the same EMF. Okay, that means it should be equal to L into di by dt. Okay, so in the place of di by dt I can write it is E by L. So writing E by L, writing here E by L1 and this is now E by L. Okay, then see what we get. 1 by L equal to 1 by L1 plus 1 by L. Right? So this is now equivalent inductance when inductors are connected parallel to an ideal battery. Okay, let us see next problem. Let's see what is the question given. A toroid is wound over a circular core. You can see diagram here. This is a circular core. On that we are winding a wire. Okay. Radius of each turn is R and radius of toroid is capital R, which is very large compared to this small r. This is a capital R and this is small r, right? The coefficient of self-induction of the toroid is given by, right? So we have to focus how to calculate self-induction. And we have learned that whenever you want to calculate coefficient of self-induction or coefficient of mutual induction, first we have to focus what is a flux. And that flux equal to L into Y. If you want to calculate M, it is M into Y. So first we have to focus here what is flux, right? Let us see now how to calculate flux. So first I'm writing here what is strength of the magnetic field inside the toroid. And this we have learned long back. Mu naught Ni by 2 pi capital R, right? This is magnetic field strength inside the toroid. Now multiply this. So flux equal to B value mu naught Ni by 2 pi R, where N stands for number of turns, right? Into area. And see what is area. It is now pi R square, right? This is area of the coil. This is a flux through each turn. Now you can see number of turns. We have n turns. So I'm taking into n. See carefully. I'm calculating now what is a flux. Okay. So B value mu naught Ni by 2 pi R into pi R square cross section area of the toroid. Right. This is giving us a flux linked with one turn. We have now number of turns n. Therefore, total flux is now into n. Right. And we are knowing that this is equal to L into I. Okay. I and I gets cancelled. So remaining what is left? Remaining what is left? Current gets cancelled. Pi gets cancelled. Remaining is now L equal to mu naught N square R square upon 2R. Right? Check it once. Mu naught N square R square upon 2R. So we have to keep in mind that whenever you want to calculate coefficient of self-induction or coefficient of mutual induction, first we have to calculate flux. Then divide that with the current. Then we are going to get the corresponding coefficient. Okay. Let us see next problem. That means that for this problem, the correct answer is mu naught N square R square by 2R. Option A is correct. I think remaining options, they are not much. Okay. See the next one. Two conducting circular loops of radii R1 and R2 are placed in the same plane with their centers coinciding. Find the mutual inductance between them, assuming R2 is very small compared to R. Right? Let us see how to solve it. First condition, it is given that both are in the same plane and centers are coinciding. That means concentric. And smaller one, which is a concentric. And see condition given here. R2 is very large compared to R1. That means inner one is R1 and outer one is R. Outer one is R. Now what are asking? Centers coinciding, mutual inductance we have to calculate. So here what I am doing is, since the condition given that R2 is very large compared to R1, first understand the purpose of giving this condition. If you calculate strength of the magnetic field at the center because of outer one, see how much weight, suppose current is I. So at the center, strength of the field is mu naught I by, it is a 2R2. This is a field strength. Now, if you multiply with the area of this one, we get a flux that is pi R1. And remember, since we are given this condition, that means throughout this loop, Okay, at any point in this loop, B value same because this area is very small. That's why we have taken directly B into area. Okay, now focus B into A. This is now flux, which is equal to M into I, right? Because the current is now passing in the outer coil, and because of this current, field is present at the center. Because of that flux linked now with this. Okay. Now I gets cancelled. Therefore, M equal to, see what else left here. Mu naught I is over. So pi R1 square upon 2R2. Right? Cross check once. It is given R1 is very large compared to R1. Wait. I think I have taken reverse, right? Cross check once. R2 is very small compared to R1. And here what I have taken. Okay, then do one thing. Let us, okay, this is R2 very large compared to R1. This is okay. Mu naught I by 2R2 by R1 square. Okay. As per this condition, the calculation what we have done, it is correct only, right? This is now coefficient of a mutual induction for this pair, right? Let us see next one. See question number 48. A mutual inductance of a pair of concentric conducting coils of radii, capital and small r. Small r is very small compared to capital with their planes inclined at 30 degree is given by. We can see this question number 47 and 48 both are almost the same. The only change is in 47 the planes are both on same plane, but in this case between their planes angle is given 30. Okay, except that everything is the same. Let us see where change comes in the calculation part. So condition capital R is very large compared to small r. When current passing the outer one, because of that magnetic field, mu naught I by, it is 2r, okay, and area of this loop, inner one, pi r. But coming to between these two loops angle, because flux equal to, we have to focus B bar dot A bar, right? This is now B into A into cos of the angle between them. So B mu naught I by 2r, A pi r square into cos of the angle. So between the planes angle 30. That means between their normals also angle is 30. Okay. It is now into cos 30. This is now flux which is equal to M into Y. Right. Then see what we get. Cos 30 root 3 by 2 and I gets cancelled. So from this M equal to mu naught I is over pi r square cos 30 root 3 by 2. Root 3 by 2. Or 2 is there. It becomes a 4. 4r. So mu naught pi r square into root 3 by 4r. This is coefficient of mutual induction for the given pair. Okay. That means you have to focus carefully. In the previous case, we have taken both in the same plane. So here, between the planes, some angle is there. That means this coefficient of mutual induction depends on the orientation of the planes, right? Suppose if you take in this question, if they are in perpendicular planes, then this becomes cos 90. Cos 90 means there is no flux. Then there is no question of M, right? That means between the coils, what is angle? It means how they are oriented. That is also important. Okay. So I hope you got a clarity.